UV visible spectroscopy. Principles: electronic transitions, chromophores, Beer-Lambert law, instrumentation, and applications. UV visible, UV-Vis spectroscopy is a widely employed analytical technique that probes the interaction between electromagnetic radiation and matter in the ultraviolet, 200 to 400 nanometers, and visible, 400 to 800 nanometers regions. It provides both qualitative and quantitative insights into molecular structure, electronic transitions, and concentration of analytes. This video presents a comprehensive overview of the fundamental principles of UV-Vis spectroscopy, including electronic transitions and chromophore behavior, the Beer-Lambert law, instrumentation, and diverse applications across chemistry, biology, pharmaceuticals, environmental science, and nanotechnology. Spectroscopy encompasses the study of interactions between electromagnetic radiation and matter, where energy is absorbed or emitted in discrete quanta. Among various spectroscopic techniques, UV-Vis spectroscopy is particularly valuable due to its simplicity, sensitivity, and versatility. It enables the analysis of both colored and colorless compounds by measuring absorption or transmission of light in the 200 to 800 nanometer range. The resulting spectra provide characteristic fingerprints that reflect molecular composition and concentration. Principle of UV visible spectroscopy. UV-Vis spectroscopy is based on the excitation of electrons from lower energy molecular orbitals to higher energy orbitals upon absorption of radiation. Absorption spectra arise when electrons transition from ground states to excited states, whereas emission spectra result from relaxation processes. Electronic transitions. Electronic excitation in molecules involves transitions between bonding, non-bonding, and antibonding orbitals. The principal transitions observed in UV-Vis spectroscopy include sigma to sigma star, high-energy transitions observed in saturated compounds, vacuum UV region. N to sigma star occur in molecules with lone pairs, for example, alcohols, amines, typically at 180 to 250 nanometers. Pi to pi star, common in unsaturated and conjugated systems. Moderate energy transitions. N to pi star, lower energy transitions observed in carbonyl-containing compounds. Among these, N to pi star transitions require the least energy, while sigma to sigma star transitions require the most. Conjugation effects. Conjugation significantly reduces the HOMOLUMO energy gap, resulting in absorption at longer wavelengths. As conjugated pi systems become larger, the energy gap for a pi to pi star transition becomes increasingly narrow, and the wavelength of light absorbed correspondingly becomes longer. For example, ethene, isolated double bond. A double-bonded molecule such as ethene absorbs light. It undergoes a pi to pi star transition. Ethene absorbs light at 165 nanometers, corresponding to a delta E of 173 kilocalories per mole. 1,3-butadiene. 1,3-butadiene is the simplest conjugated system. The HOMOLUMO energy gap is indeed smaller for the conjugated system than for isolated pi-bonded ethene. 1,3-butadiene absorbs UV light with a wavelength of 217 nanometers, corresponding to a delta E of 132 kilocalories per mole. 1,3,5-hexatriene. The absorbance due to the pi to pi star transition in 1,3,5-hexatriene occurs at 258 nanometers, corresponding to a delta E of 111 kilocalories per mole. Highly conjugated systems such as beta-carotene absorb in the visible region, imparting color due to selective wavelength transmission. With extended pi systems, the HOMO-LUMO energy gap in carotene becomes so small that absorption occurs in the visible rather than the UV region of the electromagnetic spectrum. Beta-carotene, with its system of 11 conjugated double bonds, absorbs light with wavelengths in the blue region of the visible spectrum while allowing other visible wavelengths, mainly those in the red-yellow region, to be transmitted. This is why carrots are orange. Chromophores and Auxochromes. Chromophores. Chromophores are molecular moieties responsible for light absorption in the UV-Vis region. Typical chromophores include carbon-carbon double bond, carbonyl C double bond O, NO2, aromatic rings. These groups undergo electronic transitions, for example, pi to pi star, and determine absorption characteristics. Auxochromes. Auxochromes, such as hydroxyl, amino groups, do not absorb strongly on their own, but modify chromophore absorption by increasing absorption intensity, hyperchromic effect, and shifting absorption maxima to longer wavelengths, bathochromic shift. Spectral shifts and effects. Bathochromic shift, redshift. Movement to longer wavelengths due to conjugation or solvent effects. For example, redshift occurs when a less polar solvent is used with carbonyl compounds, and bathochromic shift results from conjugation extension. Hypsochromic shift, blue shift, shift to shorter wavelengths due to reduced conjugation. For example, aniline has a maximum absorption at 280 nanometers, but when it is in an acidic solution, it shifts to 200 nanometers due to the lack of conjugation. Hyperchromic effect. Increase in absorbance intensity. For example, the addition of a methyl group to 2 positions of pyridine shows a hyperchromic effect. Hypochromic effect. Decrease in absorbance intensity. For example, methyl group introduction at the biphenyl moiety position 2 results in a hypochromic effect. Solvent effects. Solvent polarity significantly influences absorption spectra. Polar solvents stabilize non-bonding at N orbitals, affecting N to pi star transitions. Pi to pi star transitions generally shift to longer wavelengths in polar solvents. Solvent selection criteria. Minimal absorption in the measurement range. Low interaction with the analyte. Common solvents include ethanol, methanol, hexane, and water, which exhibit low UV cutoff wavelengths. Beer-Lambert Law. Beer's law, the intensity of a monochromatic light beam diminishes exponentially with the increase in concentration of absorption. Lambert's law, the decreasing rate of intensity of monochromatic light with the medium's thickness and incident light intensity are directly proportional. The Beer-Lambert law describes the linear relationship between absorbance and concentration, A equals epsilon LC, where A equals absorbance, epsilon equals molar absorptivity, liter per mole per centimeter, L equals path length, centimeters, C equals concentration, moles per liter. Interpretation of Beer-Lambert law. Absorbance is directly proportional to concentration and path length. Valid under dilute conditions with monochromatic light. Deviations arise due to high concentration, chemical interactions, or instrumental limitations. Instrumentation of UV-visible spectrophotometers. Types of instruments. Single-beam spectrophotometer. measures sample and reference sequentially. To analyze one wavelength, the single beam instrument places a monochromator in between the source and the sample, to get the beam to a reference sample as well as the sample to be analyzed. Double beam spectrophotometer simultaneously compares sample and reference, improving accuracy and stability. There is only one source in the double beam instrument. This arrangement enables more precise analysis. Double beam UV spectrophotometers are simultaneous instruments that are typically faster and more effective. Components. Light sources. UV-Vis region, deuterium or hydrogen lamps, 160 to 375 nanometers. Visible region, tungsten filament lamps, 350 to 2,500 nanometers. Monochromator selects specific wavelengths using prisms or diffraction gratings, entrance and exit slits, and optical lenses. Sample holder, cuvette. Typically, quartz for UV measurements, standard path length, 1 centimeter. Detector. Photomultiplier tubes, PMTs, amplify incident radiation signals via electron multiplication. Signal intensity correlates with light absorbance. Applications of UV visible spectroscopy. Quantitative chemical analysis. Widely used for concentration determination based on Beer-Lambert law, particularly in solution chemistry. Biochemical and biomedical studies. Quantification of proteins, for example, at 280 nanometers. Nucleic acid analysis at 260 nanometers, and monitoring conformational changes. Pharmaceutical analysis. Determination of active pharmaceutical ingredients. APIs. Drug quality control and stability studies. Environmental monitoring. Detection of pollutants such as heavy metals and organic contaminants. Water quality assessment. Nanotechnology. UV-Vis spectroscopy is essential for characterizing nanomaterials. Determination of nanoparticle size and distribution. Monitoring colloidal stability. Detection of surface plasmon resonance, SPR, in noble metal nanoparticles, such as gold and silver. The optical properties of silver nanowires depend on the shape of their cross-section. The relationship between the optical properties and the geometry of silver nanowires allows for the extraction of accurate structural information from simple UV-Vis spectroscopy. The characteristic double extinction peak of colloidal silver nanowire is a clear marker of a pentagonal cross-section, and the exact shape of the peak is extremely structurally sensitive to the radius of curvature of the edges, which is a crucial structural parameter. In conclusion, UV visible spectroscopy remains a cornerstone analytical technique due to its simplicity, reliability, and broad applicability. It provides critical insights into molecular electronic structure, concentration, and interactions. Advances in instrumentation and data analysis continue to expand their role in modern research, spanning chemistry, biology, materials science, and nanotechnology. Its non-destructive nature and versatility ensure its continued relevance in both fundamental research and industrial applications.